Welcome to the Podkey summary of Explore Numerical Computing in Swift with MLX from WWDC 2026. Today's roundup is really about one idea showing up in a bunch of useful ways. MLX Swift lets you write array-based code that stays clean, runs fast, and scales from little experiments to serious GPU work. The big themes are lazy evaluation, automatic differentiation, and a cross-language setup that makes Swift feel a lot less isolated than people sometimes assume. And the examples are nice and concrete, from Mandelbrot rendering to heat diffusion to fitting a simple curve without hand-deriving anything. One of the key design choices in MLX Swift is that array operations don't have to execute immediately. Instead, the framework builds a compute graph and waits until you explicitly evaluate it, or until you read a value that forces the result. That sounds a little abstract, but the practical upside is straightforward. You can write math naturally, especially inside loops, without constantly paying the cost of every intermediate step right away. It also keeps the graph from ballooning in unhelpful ways during iteration, which matters if you're doing repeated updates or composing bigger calculations. And this lazy model is what makes transforms like grad work so well, because the system can trace what happened and compute derivatives without you manually managing some giant graph structure. The other foundational piece is array computing. Instead of poking at one number at a time in a tight Swift loop, you operate on whole n-dimensional arrays, which is exactly the kind of workload GPUs love. MLX Swift can dispatch that work to the GPU automatically, and the same code can also run on the CPU when that's what's available. That's a pretty friendly developer story, because you stay focused on the math and the structure of the problem, instead of writing device-specific code paths and fiddling with low-level optimization knobs all afternoon. For a lot of people, that's the difference between actually trying an accelerated approach and just thinking, yeah, that sounds nice in theory. The Mandelbrot example is a great illustration because the contrast is easy to picture. A naive Swift version renders one pixel at a time on the CPU, which is very direct and very slow once the image gets big. The MLX Swift version treats the whole complex grid as an array and applies the iteration across that grid in basically 2 lines. That means way less bookkeeping code. And benchmarks mentioned there put the GPU-backed version at around 10 times faster than the scalar CPU version. It's one of those examples where the code gets shorter and the machine gets happier, which is honestly a pretty satisfying combo. The numerical method side gets interesting with heat diffusion. Jacobi iteration is easy to express because it's basically a stencil update. You average neighboring temperatures, and in array terms that maps nicely to a convolution-style operation. So it's elegant, and it's a good fit for the framework, but it converges slowly. For an n by n grid, you're looking at O of n squared iterations to settle down, which adds up fast. Successive over-relaxation, or SOR, is the more clever update rule here. It introduces an optimal omega parameter and uses checkerboard-style in-place updates, so new information gets folded in faster. The payoff is a shift from O of n squared iterations down to O of n, which is a big deal if your grid is large. There's also a nice visual side effect. You can actually see a ripple-like overshoot as the method pushes past the steady state a bit before settling in. So this isn't just abstract numerical analysis trivia. You feel the difference both in runtime and in the behavior of the simulation. Automatic differentiation shows up in a smaller, more approachable example too, fitting a quadratic curve to data. You define a mean squared error loss, callgrad, and MLX Swift gives you the gradients you need for gradient descent. No handwritten derivatives, no algebra detour, no hoping you dropped only 1 minus sign instead of 3. What's nice about that example is that it makes Autodiff feel less like a feature reserved for giant neural nets. It's just a useful tool for arbitrary loss functions, even in small custom simulations or quick modeling tasks. Another big strength here is that MLX isn't trying to live in a single language bubble. There are front ends for Swift, Python, C++, and C, and the APIs are kept consistent enough that ideas and code patterns can move across languages with minimal drama. That means you can prototype where the research ecosystem is strongest, often Python, and still ship in Swift, if that's where your app or production environment lives. Third-party front-ends extend that story even further, which makes the whole stack feel more portable and less like a one-way door. The ecosystem side is also worth noting. All the MLX components are MIT licensed and hosted on GitHub with the usual invitation for issues, pull requests, and example contributions. That kind of openness matters because it speeds up tooling, examples, and rough-edge fixes in a very practical way. And there are already related repos like MLX Swift LLM, MLX Swift examples, and language model packages showing real applications, including LLM integration and stable diffusion. For newcomers, that's helpful because you're not starting from a blank page. You can poke around working projects, borrow patterns, and hopefully contribute something back once you've got your bearings. The through line in all of this is that MLX Swift makes high-performance math feel unusually approachable. You get concise array code, GPU acceleration, Autodiff, and a path into a broader multilingual ecosystem without giving up the clarity of the Swift side. And if your first experiment happens to be a fractal, a heat map, or a curve fit, honestly, that's a pretty good place to start. This episode was generated by Podkey. Create your own at podkey.fm.